Okay, welcome to possibly the most cooked of them all. Every single differential equation from this class. So, our first differential equation, a ring with a charge lambda. So, and we have a distance right here. And so our first step is E equals, so in this case, our E is equal to KQ. Lambda is equal to dq over dr. So then we have dq equals lambda dr. So k times lambda dr over r squared. And because this is only the e in one direction, we're going to use e sine theta. And so we have a distance x from the point. And so x r squared x squared plus r squared. And so this is equal to, and what you can actually do in this situation is put the lambda back in. So that's equal to k r over, and this is equal to dq. So this is equal to q. And so what we do here is then this is actually not r, this is x. So then we get 2 pi k times 2 pi r lambda times x over x squared plus r squared. So step one, in this case, we either use sine theta, theta being this, or cosine theta, which cosine theta is this angle. So then the third step is this, the fourth step is this, the fifth step is the answer. Questions? So step one, just repeating again, so this is the first differential equation we'll need to know for physics C. The second one, E equals integral of dE. Then that's equal to integral k dq over r squared. And so that's equal to dq is equal to L times lambda. This is L. K L lambda or dl lambda over from 0 to r squared is equal from 0 to r. And because we're doing this due to a linear charged rod, our distance is actually going to be from, so that's going to be point S or R. So we're going to go backwards from here to here. So from R to R minus L. That's our bounds of integration. And that gets you in the end 1 over 4. So KQ over L. So our bounds are actually R to R minus L. So it's R to R minus L. So it's, when you integrate that, you get this times 1 over R minus L minus 1 over R. This is the second differential equation we need to know for physics C. Any questions? Any questions? Or no? We're good. Okay, looks good. I'm getting looks good, so seems good. So next differential equation, we are moving out of the electric. So just as a aside, V equals dE over dx. And so if you're trying to find the voltage in this scenario, V equals integral of KQ over L, like times this 1 minus R minus L minus 1 over R dr. And so you just do that. And it does take a bit more time, but it becomes essentially an ln function at the end. That's just a quick aside. From zero, like from our point R to R minus L to R. Then the next equation we will be going over is RC circuit. So here we have like some sort of a resistor, some sort of capacitor, and usually some sort of resistor. Does this look correct to you, Chet, of what you guys get?
Yeah, basically.
Okay, that's good. So we're gonna do Kirchhoff's law, right? So E of battery, and because Q equals CV, V is equal to Q over C. Then we do this with some algebra. Then the next step is to separate our variables. So integral of dt over RC equals to the integral of capacitance e to the battery minus q. And that's dq over that. Then when you integrate that, it's t over RC equal to negative plus c. Never forget your plus c. So t over RC negative plus c equals ln of capacitance EB minus Q. And then so we exponentiate it. And so C times e to the negative t over RC equals capacitance battery voltage minus Q. So Q of t equals to C capacitance E of B minus constant C. And so constant C e to the negative t over RC. And so at time t, there is no charge on the capacitor. C equals capacitance times E of B. So Q of t ends up being equal to capacitance times voltage of the battery minus times 1 minus e to the negative t over RC. And I, and so the graph of Q looks like this. The graph of I looks like this. And V equals IR. So voltage across the capacitor is going to go to zero as well. But I would just really focus on the first two. This sound good to you, chat? Any issues, questions, comments, concerns? Oh, by the way, if there are two batteries, yeah, so the Kirchhoff's thing is that all voltage into the circuit must equal voltage out of a circuit. So voltage in, so positive E, then this dissipates negative IR, and this dissipates QC. Sound good? It's basically all voltage in equals the voltage out, and resistors and capacitors both use up that voltage. And if there's two batteries, you just add them together. The other resistor is just so that initially the circuit doesn't short circuit. So like normally you just see something like uh so these are all equations for current through the capacitor. This is I through the capacitor. Voltage Q on the capacitor. So I of the resistor, resistor 2, so I of R2 plus I of C times R1 plus I of R2 times R2 equals E. That's how you do it for that. And you just have a resistor there always to make sure you have a resistor in the position of R1 here to make sure it doesn't short circuit. This is just one for extra information later for discharging. Okay, so next differential equation, what does chat want to do? LR circuits. So we have so I'm gonna do so after this is gonna be Biot-Savart's law, and then I think you guys should all know Gauss's law already, correct? Like Gauss's law doesn't really count as a differential equation, I feel like. So I'm just gonna go over LR circuits and then Biot-Savart's, and then that's gonna be all good. And then we're gonna be happy. If I saw a Biot-Savart problem, I'd crash out too. Too bad that was a thing. So we have our battery, right? We have our R, and we have our L. So we're gonna do Kirchhoff's law, Kirchhoff's rule here. So E equals IR minus, so actually I'm gonna reference previous work we've done on Socket Academy because I'm mildly lazy, if you didn't know that. Just mildly though. So step one, draw this. Step two, V of resistor equals V of L. E minus IR equals L di dt. Integral of negative dt times R di over E over R minus I final, giving you negative TR over L equals ln E over R I final plus C I final, and if you do the algebra, that gets you equals V over R, and this gives you the I through the inductor as a function of time. I know I kind of did it quicker, but does that make some sort of sense? Because I think Biot-Savart's law would be the worst. Yeah, Dan Fullerton, my goat, who mysteriously disappeared approximately 10 years ago, has much more detailed explanations on these. I'm just trying to go through a run through so you guys can watch this in period 2 on 2 hours of sleep. Ding. So then we are gonna do Biot-Savart's law like this. So we're gonna find the magnetic field from a loop like this at a point P in the center. This magically carries a current I, because I said so, or really it's probably easier if we do it like it's probably an easier example if we do it like this. So here we have a point P, distance A from a current carrying wire carrying current I. So we have a radius R as well. That so so dB equals mu naught I 4 pi over R squared. So R is equal to, and so sine theta, I'm going to use this as theta. Opposite, so it's just like L over, and so I'm going to treat this as an infinite wire. So ds times R ts integral of mu naught I over 2 pi from 0 to infinity times 2 because it's an infinitely long wire of mu naught I over 4 pi sine theta ds over R squared. And so that's equal to and sine theta is equal to a over r squared, so we're still gonna get the same thing. So mu naught I over 2 pi integral of, and so because the because we're gonna use the bounds, because we can say dl, that integral is equal to mu naught I over 2 pi r integral of cosine theta. So we can bring the r out to this, and that's equal to 1. So mu naught I over 2 pi r is our magnetic field. And then in the case of a funny circle thingy, which we are going to do because I feel like it, b equals integral. So in this case, b equals integral from theta 1 to theta 2 of db equals integral from theta 1 to theta 2 of mu naught over 4 pi I d theta over r. And so that's equal to integral of mu naught I over 4 pi r. So negative pi over 2, that's our angle 1, and that's our angle 2. And so that's going to be equal to mu naught I over,
Meeting's about to end, by the way.
yeah, so it becomes, yeah, so the answer is mu naught I over 4r. And so these are all the differential equations. With bias of arts law, it's really just about finding the geometric situation, and integrating it is really easy. Just do the geometric situation for all of them, for those electric field ones, and for the RC circuits, just write out Kirchhoff's law. Integrating it is easy. So thank you for watching every differential equation from Physics C in 40 minutes.